Hello.
Hi, Chelsea.
So it's my great pleasure to introduce our first speaker of this last day of session, Cesar Galindo from Universidad de los Andes, that will tell us about braided zesting and its applications. Thank you, Cesar.
Thank you, Julia. Well, first of all, thank you very much, Julia, Monique, and Leandro for the invitation. It's a pleasure to be here. It's always a pleasure to be in Buenos Aires. No, seriously, thank you. Okay. I want to talk. Oh, I want to talk about this manuscript that it was already accepted in a journal. This is a joint work with Colleen Delaney, Julia Plagnick, Eric Rowell, and Xin Shan. Most of them, they are here, so they can help me if there are any hard question. And what is the idea of this braided zesting paper? So what we want to do is a technique for construct braided fusion categories from a given one. Yeah, I will explain how is the idea. The idea, in some sense, to twist the fusion rules using two cocycles, the group cohomology, and then we have to, let's say, gauge the associativity constraints. But yeah, I want to also mention that there is a related, uh, recent related paper by Alexei Davidov and Dmitry Nikshik, when they classify the graded, let's say braided graded extension, and in some sense, part of our results are quite related with the results on this paper. I mean, we have an intersection, but yeah. Okay, so in order to describe the construction, the first thing that I need is to talk about gradients and invertible objects in fusion categories. So what is a gradient? Okay, first I want to fix some notation. Um, we will denote by C a fusion category, the set of isomorphism classes of simple objects by this letter I, and the multiplicity of A inside of A tensor B. So the fusion rules will be denoted by this letter, NABC. Okay, so one way to describe a gradient is the following. A gradient is a way to assign to the simple objects an element in your group in such a way that the fusion rules are compatible with the product of your group. In other words, if you have two simple groups, two simple objects, let's say A and B, and you fuse them, all the components will be, I mean, if you have that some element C appears with some multiplicity, then the gradient of A by the gradient associated with B must be the same as the gradient of C. That's so we are just saying that if you fuse those two elements that are gradient over A and B over G and C, then the product, the whole product, it's inside of the product of the group. The other thing that we need is the notion of invertible object, invertible simple. Here better to say simple object. So this is just an object, in this case a simple object, such that when you do the tensor product with the dual, you get that this is isomorphic to the unit. Hmm? And of course, using the tensor product, you get a group. So we have these two notions. With these two notions, it's enough to describe our construction. So we need the following data in order to apply this associative zesting. Remember that I want to, at the end, I want to construct from a braided fusion category a new one, but we are going step by step. So here, in order to do things a little simpler, I will assume that my C, in fact, is braided. It can be done in more generality, and even in the paper, this is written in a more general way. But in order to do the the things simpler now, I will do it this way. So we need a gradient, and here by a gradient also, I am assuming that this map is surjective, so it's a faithful gradient. And we need a two cocycle. This is an ordinary group two cocycle, where here by this, I mean the invertible objects graded over the trivial component of your group. Okay, that will be a subgroup of the whole group of invertible objects. And this is the two cocycle condition. So it has to satisfy the two cocycle condition. And in addition, we need a map that in most cases is just, let's say, a three coboundary. It's a map that every three elements of the group associate a scalar that we will denote in this way. Look that there is something related with the notation. We are using the same letter lambda for the three coboundary and for the two cocycle. I hope this doesn't be so confusing. But really what this function, this lambda is a morphism from the tensor product of these two objects to the tensor product. Here it should be lambda. Oh. From the tensor product. So it's a map, it's a morphism that goes from this object to this object. So that's really the map, the thing. But in many cases, this is just a multiple of the identity in many cases. And this data must satisfy the following condition. The condition is that here, look, remember here, what I am saying is I have lambda, 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 and we apply this function, this three chain in this way. And here I have to use the braiding. So we need that this equation holds. This equation, the idea of this equation is I mean, the sense is related with the following. Suppose that you have a finite group G and a faithful G graded fusion category, given an associative Zesting. So this data that I defined, remember, at least I know that I am going fast. So remember that we have two cocycle and three cochain. Okay, so the idea is with using the two cocycle, you can twist the tensor product. So we define a new tensor product when we just twist using the two cocycle here. And now the idea here is that the new associative constraint, so this part here is it's just to apply the associativity in this way, and the other, of course, in the other. So this this map will give you a new fusion category structure. So the pentagon action is exactly, I mean, can be translated in this equation. So this equation is equivalent to the pentagon, or to the, yeah. Okay, so that's why associative Zesting appears. Now, here appears a natural question. Suppose that you have an arbitrary two cocycle when there is a three cochain in such that these two maps, this lambda and this lambda, defines an associative Zesting. Well, this is the answer to this is given by, you can define a four cocycle using this picture. I mean, at the end, this is a map that goes from one simple object to another simple object that depends on four elements of your group. So that defines a four cocycle. And in fact, this in a more general way was defined by Ettinghoff, Nitschisch, and Ostrich in this paper. And here what we are giving is like a concrete description of this four cocycle. But this is a particular case of a more general theory developed by Ettinghoff, Nitschisch, and Ostrich in 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 this paper. In this paper. And the idea is that at the end, what you get using through this Fourier cycle, it's the obstruction to the existence of this of the Zesting associated with these two cocycles. So if the cohomology class of this is zero, then you know that there exists a lambda that satisfies the equation. And moreover, this forms a torsor, the set of all solutions of equivalent classes of the solutions form a torsor over H upper 3. Again, this is those in some sense, those are results on this paper. Yeah. Let me give you very briefly, because this was done in another talk, an asynchronic talk by Giovanni. Uh, so the example is testing of SUN level K. So by SUN level K, we refer to this fusion category. It's the fusion category associated with the quantum group SLQ, where Q is this particular root of the unit, and L is this particular integer. So the important part here is that the simple objects has some particular parametrization. You can parameterize, let's say, as a n tuples of non-negative integers such that the sum is equal to k, or in some combinatorial way using Young diagrams. The important part here is that it is well known. I mean, there is a canonical grading for this fusion category that can be described in any. I mean, you can. I mean, there is a way to describe a set and grading for this fusion category, and also it is well known that the invertible objects for this fusion category form a cyclic group of orders n. And there is a concrete description. I mean, in terms of, let's say, this parametrization, they corresponds to this, or in terms of this parametrization, this corresponds to this Young diagram. So in principle, we can do associative testing for SUN level K. And this is one of the things that we did in our paper. But in order, I don't want to describe with full details, but the idea is that the construction is very, very explicit in the sense that you can give a concrete parametrization of the two cocycle up to equivalence, and also a concrete description of the lambda, the three cochain. This is interesting because you can do explicit computations. I mean, let's say for this particular family. But notice that I'm saying all the time associative testing, because in general, these fusion categories that we construct, they are not braided. So the natural question that we want to see right now is when this fusion category has again a canonical braiding, some kind of braiding. So that's why we are interested in the notion of braided testing. So for braided, in order to define this notion of braided testing, I need to introduce a little more of the notation. So first, the tensor automorphisms of the identity. This is just that has this other description that is just to assign a scalar in such a way that is compatible again with the fusion rules. And one example that also it's important for the definition is the following. Suppose that you are in a braided category and you fix one invertible object. Then when you do the double twist of this, you get an automorphism of a simple object to a simple object. So that's defining a scalar. This scalar is always an automorphism, a braided automorphism of the identity, a tensor automorphism of the identity. And in fact, if the category is modular, by a paper of Jelaki and Nikshi, This give us an isomorphism between this group and the invertible elements of your molar category. Yeah. So in particular, in the case of SUN, it's again easy to compute explicitly what this chi is. Okay, now we can define this braided Zesting. So the idea is first we have this associative Zesting. So we have this 2 cocycle and this cochain. We need a function that goes from the group to the tensor automorphism of the identity. And then again, a map that goes from A times A to C star that really corresponds again to a morphism that goes from lambda G1 to lambda G2. So one of the conditions that we are asking is that the 2 cocycle is not an arbitrary 2 cocycle. It must be a symmetric 2 cocycle. This is one condition, and this is a necessary condition in order to have a braiding. And now it has to satisfy some equations. One is some kind of compatibility between the J's and this chi that I have defined previously associated with the 2 cocycles. So in some sense, this is a compatibility between the J and, sorry, between the 2 cocycle and the J that is associated with the double braiding. And the second, this is related, this equation and this equation, those are related with the hexagon equation. Okay, this is in some sense a way to rewrite the hexagon equations that later. Okay, we have here the weird part is this omega. This omega is an expression.
C and D somehow related in this equation?
C and D?
Chi lambda AB of C, and on the other side you have D.
Oh, here.
Yeah.
Yeah. Maybe I did a mistake here, and here it should be D.
Thank you.
Thank you. Yes. Yeah. That is. Yes. Thank you. And again, here, this is an scalar that again you can compute using the function, this function G, and this chi and the 2 cocycle. Well, there is again an analog result that if you have this kind of braided Zesting, so you have all this data, then you can give to your associative Zesting, so this category that you construct, a canonical or not a braiding given by these equations. Okay, this is a way to produce a braiding in your category. But this is nice, but again we have the similar question to last time, when there is a braided Zesting, because it seems to complicate this bunch of equations. But the good thing is all this equation has a cohomological meaning, so you really can solve step by step just applying group cohomology, and this is the idea of the result. So suppose that you fix an associative Zesting, then there is a braided Zesting associated if and only if, let me put more, if and only if first you can define a 2 cocycle, a family of 2 cocycles here. This is just a normal group cohomology, one associated with, by every element in the group that is greater in the category. And the first condition that you need is all of them has to, the cohomology of all these 2 cocycles should vanishes. Here is the equation. I mean, this is the way to compute explicitly the 2 cocycle. And then you can build again an element in again group cohomology of H2, H upper 2 of A with coefficient. This is the characters of your group A. And so those are the, so those are the abstractions. So the point is that if you fix one particular example and you apply these ideas from group cohomology, then you can in fact find the braided Zesting. So you can put your problem of finding braided Zesting as a pure group cohomological problem. Well, here I don't want to explain the whole notation. I think I only have 5 minutes, but this is the point. I mean, the point of this theorem is that all this equation has a cohomological meaning that allows you to compute really using techniques from group homology. And for this particular example of braided zesting for SUN level K, we did explicitly, even to be honest, in the paper we did for more general, for any cyclic gradient, we did we compute the all possible gradients. And in particular, for this case, we can give explicit formulas of everything. We can say when there exists a braided zesting. So here is a condition that is just the computation of the obstruction written in a concrete way, let's say in terms of mod, an equation in terms of mod n, but this is the obstruction rewritten. And once we know that the obstruction vanishes, then those are all, I mean, this is a parameterization of all possible braided zesting. And here we have concrete equations again for the T and for the J. In this case, the J is trivial. And even we can compute the molar data of the new molar category. So this is a way at the end, at least for this particular example, to build new molar categories in a very explicit way, because even you can say explicitly one in terms of the other, what is the molar data and other results. I want to finish saying that we even implement these computations in a package written in GAP that you can find in this repository. And using this software, you can play and compute the new fusion rules, new molar data, and even one interesting thing is that using this technique, the fusion rules can change drastically, in the sense that you obtain really new molar categories. Even the fusion rules are completely different, so they are not even equivalent as Grothendieck rings. Yeah. For example, in the case of SU3 level 3, those are the fusion graphs of, this is the, let's say, SUN level 3, and this is this one particular zesting. Well, in the paper there are more results, but we don't have time to talk about this. But one natural question is what happened with the new braided representation associated with this, because you know that when you have a braided fusion category, you have for any object a representation of the braid group. So one natural question, if there is a relation between those representations, and the answer is yes. In some sense, they are equivalent, because there is a natural, or there is a natural isomorphism between the powers of the algebra and the powers, I mean, the endomorphism of the power of the simple objects, and now applying the zesting. And using this isomorphism, you can rewrite the new braided representations in terms of the old representation and some scalars that appear naturally. Again, those are scalars that appear in the definition of braided zesting. So in some sense, up to this isomorphism is just to multiply by some particular scalar. And yeah, as a corollary, for example, if the image of the braid representation of any simple objects in B is finite, the same happens for the zesting. So that's something that in some sense was it was the motivation for the whole paper. Thank you.